the topic elements. Remember, in book 1 we learned that matter is made up of 3 basic particles, i.e. atoms, molecules, and ions. Let's do a recall of their meaning. Atom. An atom is the smallest particle of an element that can take part in a chemical reaction. Example: sodium atom, chlorine atom, gold atom. Molecule. A molecule is a group of atoms of the same element or different elements chemically combined. Example: ammonia, nitrogen gas, water. That brings us to what an element is. So an element is a substance that is made up of the same kind of atoms and cannot be broken down into simpler substances by any known chemical means. On the other hand, an element is a simple chemical substance that consists of only one kind and cannot be broken down into any simpler substances. Example is hydrogen, lithium, iron, etc. Now, every element is represented by a chemical symbol. So at this gesture, we are going to look at the chemical symbols of the various elements. Chemical symbols of elements are letters or alphabets that are used to represent the names of elements. Chemical symbols could be 1 or 2 letters. So when you look at hydrogen, it is having only 1 letter, which is its chemical symbol. When you look at aluminium, it is using 2 letters, which is representing its chemical symbol. Now, some elements also have their symbols formed from the first and third letters of their names. So when you have magnesium, the first letter is M, the third letter is G, so it has Mg. Chlorine, the first letter is C, the third letter is L, so it is having a symbol Cl. However, there are some elements that derive their symbols from their Latin, their Greek, their German or Egypt names. Example, we have copper, whose symbol is far different from what we have as its name. So Cu is its symbol. Manganese, Mn. It is important that we know the very first 20 elements, and there are various acronyms that are used in memorizing the first 20 elements. Remember that every element has its own unique atomic number with its symbol, so it is important you understand this whilst moving forward. Let's look at the next slide on the first 20 elements. So from number 11, we have sodium, and its symbol is Na, up to calcium, which is 20, atomic number 20 with the symbol Cl. Now, notwithstanding that, there are other elements which may not be part of the first 20 elements, but are used regularly, and we'll be encountering them in our upcoming lessons. So, elements like these ones: copper with the symbol Cu, gold Au, iron Fe, lead Pb, mercury Hg, potassium K, silver Ag, sodium Na, and then tin Sn. We should also learn them and memorize them because we'll be using them in our subsequent lessons. So we come to the periodic table. Now these elements, which are the first 20 elements, were not there just because they are elements, but they were arrived at through some research work, and they have been arranged and put in a table form. So the periodic table showing the first 20 elements. The periodic table is a table that shows the arrangement of elements according to increasing atomic number and other properties. Elements in the periodic table are arranged in vertical columns called group and horizontal rows called period. The number of electrons in the outermost shell determines the group in which an element will find itself. This will be explained further under the topic metals and non-metals. This is a picture of the first 20 elements under the periodic table. In reality, the periodic table is bigger than this, but we at this stage to know the first 20 elements, and this is the table that goes accordingly with it. Later in your studies in higher institutions, you will learn more about those other elements and the table as it is. So we come back to look at what the atom is. We are going to delve deeper into the structure of the atom. Now, per what we know, the atom is known to be made of the smallest particles called electrons, protons, and what? Neutrons. These particles are called subatomic particles. John Dalton was the first to put forward a scientific theory on the physical and chemical properties of the atom in 1808. Later, J.J. Thomson and E. Rutherford contributed through research to come out with the present-day structure of the atom. And that is what gives us what is known as the modern atomic theory. So these are pictures of John Dalton, J.J. Thomson, who are the first individuals to come out with the structure of the atom. And then later we'll be looking at the structure, we'll be looking at the picture of E. Rutherford. We'll be moving to the next slide soon. So the modern day atomic theory, and this is the summary of it. It says atoms are made up of three subatomic particles, namely electrons, protons, and neutrons. The protons are positively charged and the electrons are negatively charged. The neutrons have no charge. They are neutral. The protons and neutrons are in the nucleus. So here comes the picture of E. Rutherford. So after these three scientists had worked, this is the structure of the atom as we have it. Okay, so you have the nucleus at the center, you have the electrons which are in the shell moving around it. So the subatomic particles are the proton, neutron, and then the electron. So this is how finally the structure is. So you have your electrons, neutrons, and then they are in the electrons are in the electron orbit with the protons and neutrons in the nucleus. Let's move to the next slide. So by virtue of that, we describe the atom as spherical in shape. The atom is made up of two main parts, namely the nucleus and the outer shell. The nucleus contains positively charged particles called protons and neutral particles called the neutrons. On the other hand, on the outer shells are fast-moving negatively charged particles called electrons. The fixed path around the nucleus along which electrons move or orbit is known as shell or energy level. Now let's look at the diagram of an atom. So in our drawing, we are not going to draw the structure we saw earlier, but this is how we're going to draw our structures moving forward for an atom. So generally, an atom with 6 electrons will be drawn this way, with 2 shells, and then with the electrons positioned at the various parts of the shell, and then the nucleus having the protons and the neutrons. So this is the part that you are supposed to know. Now let's come to this table where we are looking at the mass and charges of the subatomic particles. So in summary, protons are represented with the symbol P with their relative charge as +1, and then their mass is 1 AMU, which is the atomic mass unit. They are located in the nucleus. Electrons is with E, negatively charged with a mass of 1 out of 1,000, 1,840. I repeat, 1 divided by 1,840, and that is found around the nucleus. Then we come to the neutrons, N. They are neutral, so they have a charge of 0. The mass is 1 atomic mass unit, and it is found in the nucleus. So let's proceed. Now let's look at a neutral atom. A neutral atom, there are equal number of protons and electrons. Thus, the atom contains equal but opposite charges which cancel each other. So when you are asked the question, why is an atom electrically neutral, you will say that they are neutral because the number of protons and electrons are equal, and for that matter, their charges cancel out each other. Let's go to the next slide. Now in the next slide, we are going to look at the representation of subatomic particles. Subatomic particles of an element can be represented by its atomic number, mass number, or neutral number. So atomic number. Atomic number is the number of protons in the nucleus of an atom. It is represented by the symbol Z. Atomic number is also known as the proton number, where it is represented by P. Atomic number is also equal to the number of electrons of that atom. All atoms of the same element have the same atomic number. Okay, so come to mass number. Mass number is the sum of protons and neutrons in the nucleus of an atom. So it is represented by the symbols A. Mass number is also known as nucleon number. Bear in mind, they are all found in the nucleus. So the materials that are found in the nucleus are called nucleons. So that is the nucleon number. It doesn't matter whether it is a proton or a neutron. The neutron number. This is the number of neutrons in the nucleus of an atom. It is denoted by the symbol N. Atoms of the same element may have different neutron number. Let's now proceed to look at how these are represented. So you have on your left side. So this X is representing any element, the symbol of any element, the chemical symbol. Then the A here is representing the atomic number. So that is where it is written. And take note, the A represents atomic, the mass number. I repeat, the A represents the mass number, while the Z represents the atomic number. The Z is written as subscript on the left hand side of the chemical symbol, whilst the mass number A is written as the superscript of the chemical symbol. Then here is a typical example. So we have lithium with the number 7 as the mass number, where there is the 3 here, and then the proton number is 4. So it makes the mass number 7. So the atomic number is 3 plus that 4. So that is what we have here. We'll pause here and then continue on the next slide. So we are going to look at the relationship between mass number, atomic number, and neutron number. The mathematical deductions that we make is that the mass number is represented by the symbol A, the number of neutrons by N. In general, the mass number is represented as is equal to the Z plus N, where the Z is representing the atomic number and then the N is the number of neutrons. Now from the general formula, we can make the following deductions. Mass number is the same as the number of protons plus the number of neutrons, where we shall have the symbol Z plus N. Number 2, the number of electrons is always equal to the number of protons and the atomic number. 3, the number of neutrons can be found by subtracting the atomic number from the mass number. So here we have mass number minus atomic number. So when we come to the next slide, you'll see the representation of what we've just done. You have the structure here where you have 2 electrons. You look at the nucleus, we have 2 positive charges there which represent the protons, and then 2 neutrons. And so we want to represent that. You have the symbol for helium, which is He, the superscript 4, which is the mass number, and then the subscript 2, which is the atomic number, which we also refer to as the proton number or the number of electrons. So let's take a look at an example. Now the atomic number of an atom X is 17 and its mass number is 35. Indicate the number of protons, electrons, neutrons in the atom. So in solving this, we shall have the solution as such. I, the number of protons is 17. Now the reason is that the number of protons is the same as the atomic number. So if the atomic number is stated as being 17, automatically the proton number is also what? 17. The number of electrons is also 17. This is because the number of protons is always equal to the number of electrons in a neutral atom. And then the last, which is the number of neutrons in the atom. Now the number of neutrons is always equal to the number, which is the mass number, minus the atomic number. So here we have 35 minus 17, giving us 18 as the number of neutrons. Now proceed. Now the representation of atomic number and mass number of an atom. We have had some idea about how it is represented. So let's just go on. Now to indicate the mass number and atomic number of an atom, the atom or element is denoted by a symbol X. So then the mass number A is placed at the upper left superscript. So that is what we have here. So this is the superscript upper left of the symbol X, which is representing a particular element. Now the atomic number Z is also placed at the lower left subscript. Example X, okay, which is the element symbol, and then the Z, which is the atomic number. So in all, we can say that the atom is therefore represented by an X and what you have seen here. Now where A is the mass number, the Z is the atomic number, and the X is the atom. So let's go on and look at an example. Example 1. An atom of aluminium is represented as 26 superscript 13 subscript Al, the symbol of the element. This means that aluminium has a mass number of 26 and an atomic number of 13. Example 2. Now in example 2, we have the element lithium with the symbol Li, having a mass number of 7 and an atomic number 3. I represent the element. I calculate the number of protons, and then electrons, and then neutrons. So we have the I, the mass number represented by 7, the atomic number represented by 3, and then the symbol. So the number of protons. The number of protons will become 3 because the atomic number is 3. Since we know that number of protons equals to the number of the atomic number. B, in a neutral atom, the number of protons is also always equal to the number of electrons, and therefore the number of electrons will be equal to 3. Whilst in the last question, where we are looking for the neutron number, we have the mass number equals to atomic number plus the neutron number. So we subtract the atomic number from the mass number to get a value of 4. So that is how that is also represented. Let's proceed to look at another term used when we talked about elements, and that is isotopes. What are isotopes? We talked about twins, and we can talk about identical twins and non-identical twins. Now some elements are there may be slightly different from the other, just like how we have twins that are non-identical. So in defining what isotopes are, we say that isotopes are atoms of the same element which have same atomic number but different mass number due to differences in their number of neutrons. Now that means the number of neutrons vary from an atom to another atom but of the same element. That is where you have the mass number becoming different. Another alternative definition for isotopes states that it can be defined as atoms of the same element with the same proton number but different neutron number. This diagram here shows a typical example of what an isotope is. So this is a carbon atom. Now this carbon, you can see that the atomic number is 6. This is also 6, but this one, the mass number is 12, and the mass number of this one is 13. Now what it means is that the neutron number for this is different from the neutron number for this. That is what has resulted in the different mass numbers for the same element. So we can also talk about isotopes of hydrogen. So here, look at the central part, which is the nucleus. Here we have only one proton. Here we have one proton and then one neutron. Here we have one proton and one proton and two neutrons. So for this, its mass number is 1, its mass number is 2, and then its mass number is 3. So that is a typical example of isotopes for hydrogen. Let's come to another one which has to do with isotopes again. So we come back to isotopes of carbon. So when you look at carbon, you see that the number of neutrons should be equal to number atomic mass minus atomic number. So here we have number of neutrons. So here its neutron number is 6, this one is 7, and this one is 8. That is the isotope of carbon. So pause here, and then we shall proceed to look at the next slide. Now from this slide, we are going to look at how electrons are distributed in an atom and what we refer to as electronic configuration. Now electrons orbit or move around the nucleus along a fixed path called the shell. We've learned about that. A shell can also be defined as the path through which an electron moves. It can also be defined as the energy level of electrons. The shells are represented by letters like E, K, L, M, N. That is what it is used to represent them. So we use the alphabet, and it starts from K. So you cannot just allot any alphabet on your own. You would have to use that of what the scientists have generally agreed on. Now each shell is capable of accommodating a certain number of electrons, and we are going to look at that. So here you have it. Distribution of electrons in different orbits. So this is our nucleus. Now the very first shell around is the shell K, and it can carry a maximum of 2 electrons, followed by the L shell with 8 electrons, with M shell 18, and then the N shell with 32 electrons. So the first shell closest to the nucleus is referred to as the first energy level. After that, the one following it is the second energy level, through to the fourth energy level. So this is distribution of electrons in different orbits. So we proceed. Now the relationship connecting the maximum number of electrons in a particular shell is given by the formula, and this formula states that number of electrons is equal to 2 n raised to the power 2, where n is equal to the number of shell. So if we look at what we just did, First shell will have 2 into bracket 1 raised to the power 2. That will give us 2 electrons. The second shell, L, will also give us 2, and so where n is the number of shell placed in the 2 squared, the total number gives us 8 electrons. And then we have the third shell giving us 18 electrons. So it follows by that formula. So we proceed to look at what is known as valence electron. Now, when you fill the shells of an atom, the last shell, outermost, may contain some electrons, and so that electron is what we refer to as the valence electron. So a valence electron is an electron on the outermost energy level in an atom. So here we look at a typical example of what we have for oxygen. And oxygen is having 2 shells. The first shell can carry a maximum of 2. The second shell can carry a maximum of 6. What it means is that in filling these shells with electrons, you must make sure that the first shell is completely filled before you move to the next shell, and that shell must also be completely filled before you can move to the next shell. So for oxygen, we have 8 electrons and it is having 2 orbits. Let's go on. So with chlorine, this diagram, so you can see the electrons in the orbits. Okay, so at the end of the day, the electronic configuration of chlorine is 287. What that means is that the first shell carries 2 electrons, the second shell carried 8 electrons, and the third shell carried 7 electrons. Okay, so let's look at some worked example. An atom 18. An atom has 18 electrons and neutrons and 17 protons. So the question is, how many electrons are in the atom? What is the mass number of this atom? And then you should draw the structure of the atom and show its electronic configuration. You state the possible name of the element with atomic number 17. So here is the solution to the question. Now the number of electrons will become 17. Its mass number, as we did already, 17 plus 18 will give us 35. And then for the question C, you refer to the diagram here, which shows how to draw the structure of the atom, chlorine. Now the element and then its electronic configuration. Then the element which is the D, the element with atomic number 17 is chlorine. We are going to look at another very controversial part known as formation of ions. Now, when it comes to the formation of ions, they are formed when an atom gains or loses one or more electrons to become electrically stable. And when it loses electrons, it comes with a certain character. Likewise, if it gains electrons, it comes with a certain character. So an ion is a charged atom formed when an atom gains or loses one or more electrons to become stable. When an atom gains or loses electrons, it becomes charged. There are 2 types of ions, namely cations and anions. So we're going to look at them. Cations. Cations are positively charged ions. They are formed when an atom loses one or more electrons to become stable. Now, most metals form cations. Let's look at this diagram. So, how this cation is formed. The element here is aluminium. So, when aluminium is neutral, its electronic configuration is 283. So, the last shell will carry 3 electrons. Now, because it is having 3 electrons, it is not stable. For it to be stable, it must lose these 3 electrons to become stable, and that is what brings it to this point. So from 283 to 28, the last shell here has been removed. However, that 3 electrons are not lost. It still belongs to the aluminium atom. So you can see here now the charge. So by virtue of that, aluminium will lose 3 electrons. So here when we have a neutral atom, plus 13 minus 13 equals to 0. So that makes the charge 0. So it is neutral. But here, because it has lost 3 electrons, the number of electrons left are 10 when you count the number of electrons in the shell, and that will give us minus 10 electrons as against the plus 13 protons. So virtually we have plus 3. So aluminum will have a charge of plus 3. So you can see it here. So this aluminum, it loses 3 electrons. So these are the electrons it has lost, and then it is possessing the charge of plus 3. So we're going to continue from there. Now, so we're going to talk about another cation, which is the cation of sodium. Now you can observe that we have 3 shells, with the last shell having 1 electron in it. Now that becomes the valence electron, so it loses that one, and it becomes 10 electrons in the outermost shell with only 2 shells. So like I said earlier, that electron is not lost, so that makes it to become a charge of plus 1. So that's what we have here as a charge of sodium. Let's proceed to the next slide, and where we are going to talk about anions. Now, anions are negatively charged particles. They are formed when an atom gains electrons, and mostly non-metals form anions. Let's look at the structure of it. So this is a typical example of an anion and its formation. So we have here chlorine. Now chlorine is having 3 shells, with the last shell carrying 7 electrons. But here, because of the number of electrons in the last shell, chlorine will need 1 more electron to make it completely filled. And so it maintains its 3 shells and then brings in an additional electron from some other element. You have plus 17 minus 17 gives us 0. But because we have borrowed from outside, the number of protons will still be it should be 18, and then the electrons should become 18, and when you add it up you have a charge of minus 1. So it makes chlorine have a charge of minus 1. Another typical example of the formation of ions is that of the element with 2 electrons in the first shell and 5 electrons in the outermost, 7 electrons in the outermost shell, and that is fluorine. So fluorine has 9 protons, 9 electrons. That makes its net charge to be 0 because it will cancel out. But here, when the 9 protons are here, we've added 1 electron to it to make its shell completely full. So it makes its net charge to become negative 1. So that makes this particular material an anion. Now the last but not the least major heading is valency. Now valency is said to be the combining power of an element. Now the valency of an element is numerically equal to the number of its charge. The valency of an element can also be determined from the electronic configuration of an atom. Elements which have between 1 and 4 electrons in the outermost shell have the valency equal to that number of electrons. For example, we have carbon with 2 and 4, so the last shell is 4, and therefore makes its valency to be 4. You have aluminum 283, the last shell is carrying 3 electrons, so its valency is 3. Calcium 2882, valency is 2. Now elements which have between 5 and 8 electrons in the outermost shell have their valency calculated as the number of electrons that are needed to complete the outermost electronic configuration, and it is calculated as valency equals to 8 minus the number of electrons in the outermost shell. So any number of electrons which is 5 or more, you subtract it from 8 to get the value of that particular element. So the valency is calculated as such. But if the number is between 1 up to 4, you maintain the number as the valency of the element. So this is how one simple way by which you can determine the valency of some elements. So we have A1, so that's group 1. Now group 1 elements have 1 electron in the outermost shell, so their valency is 1. Those in group 2, they have 2 electrons in the outermost shell. Those in 3, like that. But when it comes to 4, it is 5 or more, so you subtract the 5 from the 8, you get 3. If it is 6, you subtract from 8, you get 2, and then it goes on to the last shell. Now it is important we learn about this. We're talking about radicals, and radicals are basically a group of atoms which stay together with a common charge or combine as a charged unit. We are to memorize this and know their valencies. So you have hydroxide with OH minus 1, nitrate NO3 minus 1, hydrogen carbonate HCO3 minus 1. So with the other ones, you need to study them and then master them. Now, a simple trick on how to memorize the valency of radicals: you just basically take the charge of it, and then when you take the charge, the number associated with it becomes its valency. As simple as that. Then we come to, so the last part of it is you subscribe to the channel, the Best Size channel, if you have not yet done so. May God be with you.